I'm an SRE at Google. I've been on call for a lot of different services, and this is a talk about being on call and about operational overload and how to overcome it. And yeah, the trick is with SLOs. A few years ago, I was on a storage team, and they're under a lot of pressure. There's a lot of operational load going on in the team. The pager load was incredibly high. Ticket load was incredibly high, and our user complaints was also pretty high. As a result, we were pretty unhappy. And, even though we wrote the book on best practices, as William Gibson says, the future is here, but it's not evenly distributed yet. And that's how I like to describe some things inside of Google. There's various levels of maturity going on inside. And at the time, we were not a very operationally mature team. Around the time that this was happening, I posted this tweet on New Year's Eve to the on-call selfie hashtag that Alice Goldfuss had started, and she featured me in her talk at Monitorama in 2017. This is an example of somebody on call relaxing with their family, and the 2016 leap second is about to happen. In Australia, the leap second happens about 10 a.m. the next day, so I'm very excited. The leap second's about to happen. The truth is, in this photo, I'm burning out, but I don't know about it yet. So this is, it's ironic that I was used as an example of somebody relaxing with their family while being on call, because that's actually not what was happening. I used to like being on call, and I really enjoyed the feeling of troubleshooting and getting to know a system and poking around and making it work again. But I didn't like that anymore, and I really felt like this huge anxiety was coming up on me as my on-call shifts were about to start. All the work we were doing while on call was kind of robotic work, the same things like, oh, this page shows up, you do the exact same motions, you restart the server, and you cross your fingers. And I didn't think that's how it should be, but that's how we ended up, and it was really hard to get ourselves out of that situation. And I didn't believe that going on call was something that you did just for the sake, like you're a system administrator and that's your job, so here's the pager. I think we go on call because that's a tool that we have to keep the reliability of the services up. If we didn't have to go on call, then there's absolutely no reason we should do it. But we have great brains, and we can automate a bunch of stuff, and the brain should be used for pattern matching and problem solving and doing stuff that hasn't happened before. But anyway, our pager load was so high that we were ranked the 100th percentile worst team in Google 2 reviews in a row, and it's funny now, but it wasn't funny at the time. And so upper management gave us explicit instructions and lots of air cover to drop everything else we were working on and focus solely on getting our pager load down. So this is a talk about one of the things we did to refocus our energies, look at how we can focus on only the problems that mattered to the users and realign our expectations with those users. And by realigning expectations, I mean paging on what users care about and not what was broken at any point in time. And then that meant we had more time to improve the system because we had a lot more time on our hands. Anyway, we'd known about this technique for about 10 years. Ads invented this technique 10 years ago, and I knew about it, but I always thought it was a way of measuring your uptime in quarterly reports and saying, hey, managers, we're doing a great job, and not as a way for actually day-to-day iterating and getting your service better. So I've got this idea that anything in operations sucks as the size of the system increases, and at the same time, the size of the human size of the team does not change. Anything that grows more than sublinearly as the system grows means operations sucks. So every time you get a ticket in response to some event, obviously as the system gets bigger and that ticket happens more frequently, then there's more work to do. Even though the percentage of work as the system grows might stay constant, that absolute value gets bigger and bigger. And there's this cap out of the size of your team, the number of hours you can work in a week, and as to what you can do in response to those tickets. So if the ticket takes the same amount of work every time, then obviously more tickets shows up and there is more work to do in a week. But as the system grows, you don't get more people magically. So the team doesn't grow super linearly either. Now we know in Google, in the SRE book, we talk about this idea of capping ops work at 50% of a team. And that means that there is a buffer of room within the team to focus on making project improvements to make these tickets go away. But what happens is the rate of change of these systems is so fast, and the system grows so fast that you really have to pay attention to this and get on top of it early on and automate everything and make those tickets go away, make the pages go away. But that has the side effect that every bit of automation or diagnostic you build into the system can also become technical debt, because as the system changes rapidly, the things you built for the service a year ago that were really important to you now do not have the same advantage anymore, that could like hinder your progress. So I have this idea that a bad diagnostic alert is like a bad unit test or a poorly designed API, and there's this tight coupling between these two things where you say, I really care that the disk space isn't running out, and that's totally fine when the system is small, but maybe it doesn't matter anymore when you've got hundreds of thousands of disks. So as these things build up, then also removing them takes time, because there's a lot of fear and uncertainty about why they existed in the first place. And so you have to invest time to remove parts of the system, and anyone who's done a system turn down knows this is true. So I also assume that you're also trying to spend your time maintaining the system being monitored and not just the monitoring as well. So there's usually very little time to maintain the monitoring of the system anyway, which is why monitoring ends up sucking a lot. So I guess the thesis of my talk is I want you to spend almost no time investing in the monitoring itself and focus on a very few constant number of alerts for your whole system that actually matter to you and the users of your service. And that small set of expectations doesn't depend at all on the size of the system. So another thing we talk about in the SRE book is that paging on a cause is a recipe for disaster, because and alert fatigue. Because even though some of these things might be quite valid problems, how many of them actually matter to the end user? And if you've built a system that is resilient to small outages, then a lot of the times this is just noise, and it doesn't impact the user straight away. And these alerts are compelling because they tell you what the problem is straight away. Like, it's nice to have a little diagnostic alert saying you're running out of disk, or that the disk in the RAID array has started to fail. But my team in storage had tens of thousands of disks, and so we didn't page directly on disk failures, but we did page on things like the availability of parts of the database, like whether certain key ranges were available for unavailable for too long, or the replication between data centers was too far behind. And so I guess the question is, were these symptoms of our system, or were they causes? So I guess there's another question, which is, what is symptom-based alerting? So a symptom is kind of knowing what is wrong, knowing that something is wrong rather than what it is. And you can compare this to going to a doctor. If you go to a doctor and say, I have pain in my lower back, or I've got a sore throat, you don't go and say, I don't bend with my knees when I lift my child, or there's another cold going around daycare. The doctor usually is the one who goes and figures out what is actually wrong with you. You just tell them the parts that are hurting. And likewise, I'd like to find out from a system that the error rate is too high, or latency has gone bad, or users are unhappy, rather than there's a disk that's failed or there's packet loss. Because I expect packet loss to happen all the time, and I expect disk failures to happen all the time. But then again, maybe that's just me, but we are at a large installation system administration conference, so I assume that everyone else has a large number of disks as well. So I guess then I still haven't answered the question that what is a symptom-based alert? Was this key range is unavailable a symptom? And the answer is, it is to me, but it's not to my user. It's a matter of perspective. We can tell that an alert is a symptom-based alert or a cause-based alert because you look at what the service is supposed to be doing for somebody, and if the users are having a bad time or as a result of that thing, then definitely that is a symptom. But anything inside of that service boundary is a cause to the user. The users don't care that part of the key space has gone away and that's why their latency has gone bad, or the RPC queue depth on a particular server has blown out. And if the users aren't having a bad time because the queue depth on a particular back end has blown out, then I don't think I care about that either. So you've got to ask, how do we get the user's perspective on whether or not they're having a bad experience without them having to call up and say so, because we still want to have monitoring systems to detect these problems before the users notice. And before I answer that, I want to take another quick detour, which is we have this system, we know parts are failing and they fail all the time. And we've also identified that we don't want to page on all of those things failing or any single piece of those things failing all the time. We only want to page on things that matter. We want there to not be very many things about how we decide whether to page or not. So what I guess I'm getting at is how much failure is acceptable before you think you have to page. And there's a clue in this picture. We know this term by other names in different fields. There's some amount of variance in the acceptable level that you deliver to a customer. And in the SRE book, we call this error budgets. The smaller the budget, the tighter the tolerance. Also in web operations, you can expect to spend this budget. You've got to track how it's spent, and if it's getting close to tax time, you know, the half price on every error. But we also know that the budget gets spent for you because there are bugs in your own and the other systems that depend on you and that you depend on. And then you've got users who show up all at the same time and behave unexpectedly. And there are natural disasters that you can't predict. And then, of course, there's you. And there's a great thing about being on call over New Year's Eve. It's that nobody's touching the system. So there's no change going on, which means that the chance of anything going wrong is very low, and you don't get paged. So assuming that you haven't lost every single one of your available errors to spend because of all these other reasons, you have some left over, and you can play with them, and we call that testing and production. But recognize that if we don't set our expectations and use these errors to our advantage, then they're also lost because users will come to expect a certain level of performance, and if you don't spend your error budget, then you've actually not got that error budget to start with. But there's a tool we can use to set our expectations, and we call that the SLO. So this is an abstraction against the service. It's not defined under the hood of how a particular implementation is built, but so we don't need to know the intimate details of the composition of the service. But we can expect that given a certain type of request to the server, it will perform in a certain way. And users higher up on the stack who depend on you can engineer their service based on the SLOs you provide. People will build against this service level. But as I was getting at, the user of a service will expect that the service level applies to... sorry, I wasn't getting at that at all. What I want to say is that users expect the SLA, the SLO applies to them and them alone. They don't think there are any other users, and you can't say to a user, this is the SLO I give across everybody, because the big users will dominate that and the small users will have high error rates that you can never notice because they're lost in the noise. So everybody has to get the SLO individually in isolation. I found this quote when I was looking for doing some research about the talk, and I thought that resonated because people then go, well, okay, obviously the answer is SLOs, but how do we pick them? And there's a lot of different factors involved in trying to pick a tolerance level or an SLO or the error budget size. So how do we pick our own? We can measure our current performance, and that's a good baseline to start with because that's what the system is currently doing, and the users, you will either know that they are happy with that or they're not happy with that, and so that sets a place to start. You can look at your operational load, your support tickets, the number of pages coming in, and decide if that's an acceptable level for your team. And if that's too high, you can lower the expectations of the service so that things don't file tickets or don't page as often. And you can also negotiate with the users or your product management to decide whether or not the level of service being provided is acceptable for the users, if it's making the company money, or if there is the ability to lower or raise. But when in doubt, and this is what I was getting to before, when in doubt, the SLO is the status quo. So if you don't have an SLO, the answer is you do in fact have an SLO, but you don't know it yet, but your users do. So people always come to expect better performance than the advertised SLO if you continually exceed your SLO. And also superstition arises from not tracking the SLO directly. because at that point, you know that the users are expecting better performance than what you advertise, and suddenly all of the ability to play with that error budget goes out the window because every deployment comes with somebody going, oh, hang on, we can't do it that way because the users get unhappy. And then you have to ask the question, are we actually measuring the right thing now? So there's a lot of risk aversion and confusion if you don't stick to the SLO and you spend the budget and let the users come to expect what the actual level of service you're willing to provide is. So now we have an SLO, we can easily define what a symptom looks like because we have this objective of what the service is trying to do. And so a symptom of a problem is now any time the SLO is not being met or in danger of not being met. Which now answers the question, how do we make a symptom-based alert? You program against the SLO. Now for any system, the availability is the uptime over the total time it's been up. So a system with a target of 4 nines can be down for about 52, almost 53 minutes in a year and stay within its availability target. But distributed systems are quite complicated. And if a microservice crashes in the cloud and no queries are in flight, does it make a sound? So computers, and especially queries, are much easier to model with discrete maths. So we can convert our function to something that's much easier to measure. And we can say things like the number of successful requests that have come in and been returned to the user over the total number of requests that have come in is our availability. So a 1 million requests in a day of a 4.9 service means that you can serve up to 100 errors in that day and still hit your target. And how do we measure this? Well, it's very easy. You just write some code. You stick a little counter, the little metric in your app. And you can count the response code broken down by any number of dimensions that you like. So maybe we want to respond measured by the response code and the user that the request came in. Because remember, we want to make sure every user gets their own SLO, so it's important that we measure the performance by user. I want to stress that it's hard to do this outside the application. It's very easy to do this outside the application with an external prober, like a Nagios check. But it's not very useful at high query rates because your sampling rate gets lost in the noise. And as the query rate increases, the usefulness of your sample is the opposite of that. I've totally forgotten the word. The inverse, thank you. So you can see that the area inside that box is totally represented by that one sample, and there could be, depending on the size of your service, if you're doing like 10,000 queries per second, then that's obviously 10,000 things represented by that one sample. So you can make assumptions when the probe is failing that you're failing generally, but when your probe is succeeding, you can't make very many assumptions about whether or not the service is performing well. So a better place to do this is by measuring at the load balancer, because if a back end goes away, you still have the metrics from the load balancer, having received a request and passed it on and waiting for the response to come back. Okay, so you build a system, you start with your favorite time series monitoring system, you collect and you compute the availability of the system, and you call that the SLI. You measure that value over a time period, you call that the SLO duration, and then you report if the measure goes over a threshold. And that's basically it. This is sort of mostly Prometheus rules. But there's a problem here, which is that it's very noisy to alert on the instantaneous rate of change, because you can get a high burst of errors in a short period of time, and that might not be a problem to you because your error budget is big enough that it smooths out across small bursts. And so you don't want to get paged quite frequently, because that's kind of the whole point of this talk. You instead want to page when the rate of consumption of errors goes up too high. So we kind of want to predict the future. How many errors do we expect to be able to handle, and how many do we expect to get? And so we can make an alert instead for the rate of consumption or the rate of change of errors over time against an estimation of how much we have available to play with. And we call that a burn rate. And so we alert if the burn rate means we think we're going to exhaust our error budget sooner than we should. So an error budget of about 1%, like a 2.9 service, that does 1,000 queries per second or requests per second means you've got 10 per second of errors you can play with. But over a longer period, like a week or a month or a quarter, the kind of timescale that you're actually reporting these things to customers, the total number of events and the tolerance for errors is much greater. So for example, if we want to say that our SLO is a week, and we have something like, 86400 times 7 times 1,000, which is that number, and 1% of them is available to burn, that's like 6 million permissible errors in a week. But, you know, after a week, like if you're going to burn your error budget in a week, then that's kind of a long period of time to, a long amount of information to keep in a time series database. So maybe you want to say a pageable offense is something that needs response in the next 24 hours. So we can measure that rate over a shorter period of time, and we're basically scaling that previous number of 6 million over a week to a shorter amount of time. Say, if we think we're going to consume all 6 million in one day, then that's clearly bad. So maybe we say we set the alerting threshold to 70 errors per second over a shorter period of, say, 10 or 15 minutes. So if you consume 15 minutes of information and that's 70 errors per second, and I'm sorry the units also confused me the first time I thought about this, then perhaps you can burn 252 errors in an hour, and if that's happened, then you fire an alert. Hopefully this graph is a little bit better at explaining it than I am. We want to scale our error budget down to a 1 hour window of 252,000. And we know that our SLO error rate is 10 errors per second, but we're setting a paging threshold of 70. And the reason for the distinction is there's a high chance that I need to respond immediately to a 70 error per second burn rate over an hour period. Or I've written 15 minutes there. So let's say if the 15-minute rate goes over 70, then I've got 15 minutes of delay before I get notified that there's a problem of a high burn rate. And the 70 means that this is definitely a problem that is going to consume all of the errors in the next day. And that means we blow the total budget for the rest of the week. But if we page at the 10 errors per second rate, then we will know about more SLO violations, but they're going to take a little longer to, well, there'll be more of them, right? And so some of these ones don't necessarily need to page because a burn rate of 10 errors per second means we're going to hit our target at the end of the week, and maybe that's okay. So you set the threshold a little bit higher. And if it sounds like this is dark magic, it kind of is, because we're also just estimating the size of the budget, and there's a lot of fudging going on. So you set the threshold just high enough that everything seems okay. And the other great thing is, because this is a negotiation with your users and your product and the team itself on what the values are anyway, then you have a lot of room to be flexible here. All right, so a fast burn alert would be written in Prometheus kind of like this. So we have a computed value of expected events over the next time period and what the budget is and how fast we want to burn all of those errors before we set a page. That's the burn period. So we do have demo. And demo, God's willing, this will go smoothly. So I've got 10 backends running and a little load balancer, and these are deliberately badly written. So it's a round robin. I'm currently running a small load generator against it. So it's just round robining again between the backends, and I've got some alerts set up. All right, thanks demo gods. That's not supposed to happen yet. And we can go over to my little Grafana window. So on the top left, we're estimating how many total alerts we can receive in the next week based on the current input. So if the input request rate is, let's call it 100 queries a second, because I think that's what it's set to, then we can estimate that there's something in the order of 4 million, I think, I think we're currently ramping up. But does that make sense? We're taking the current request rate per second and multiplying that by the number of seconds in a week to get an estimate of how many queries we're going to get over the total week. based on the current point in time. And then we divide that by the error budget. And that gives us what our error budget target for the week is. And then we divide that again by the burn rate to get us the alerting threshold, which is the yellow one in the bottom left chart. So the alerting threshold is based on the incoming rate, the error budget set, and the SLO period that we've defined. So if our instantaneous rate or our 15-minute rate, or I think for this example I've set it to the 1-minute rate, exceeds that alerting threshold, then the alert is going to fire. So you can see it ramping up because our query rate is increasing. On the flip side, the error rate, the current error rate, is just the number of errors coming in right now, and you can see the burn rate at the bottom is the green line. So the cumulative errors is going up because there are errors in the system. The backends are deliberately designed to fail about 1% of the time. And so we've got a 1% error rate. Now I think I've set the threshold to be 10% of the incoming queries just for because the demo was small, I wanted to get the numbers sufficiently separated that the demo would work. So what I'm going to do now is run an antagonistic load generator, and it's going to try and DOS the system. While I wait for that to warm up, if there are any questions, feel free to step up to the mic or yell them out and I'll repeat them. Okay, good. I think everyone's following along then. Yeah?
Is Prometheus the monitoring software, or is it just what's collecting it on the back end from your monitoring pieces?
Prometheus is doing both. So the question was, is Prometheus the monitoring or the collecting software? It's currently doing both. I'm using Prometheus to scrape the metrics off the back ends and the load balancer. And it's also computing these synthetic time series, and it's also generating the alerting rules. So it will fire off the page once when the demo succeeds, if the demo succeeds. All right, so I think that's kind of warm now. So what I'm going to do is replace one of the backends to one that fails more often. So it's going to start failing at, I think, a 10% failure rate. But because it's only one of the backends, I think it's going to only change the rate of the cumulative errors, that gradient, which means that our burn rate will step up a little bit. Or my demo has gone horribly wrong, and instead it is... No, that was good. All right, so our error rate has stepped up, and all right, so the error rate stepped because I killed the back end and it was all sending queries and not getting a response for a little while. But you can see in the lower left chart that the current rate of burn is now up to 30 from previously 10 errors per second, which is good, right? We've got a backend that's failing more often. Let's say we've done a rollout of new software, and this backend, this new version of the software, has a higher error rate for some reason. If you really squint, you can see the graph in the top right has changed gradient between that new line and the older line. It's kind of hard to see from basically everywhere. But so we have to trust that our derivative down here is telling the truth. And also is the incoming query rate, because the antagonistic load generator is still running, you can see that our threshold for errors has increased because the incoming request rate has increased. So we're computing a prediction over the next 7 days or whatever I've set it to for what's available as our SLO budget, our error budget over the next SLO period, sorry. And that's gone up, so it means we have more room to play with, right? So the next thing is, let's say there's a crashing bug in this new backend, so I will just turn it off. Oh dear. Let me try that again. It did? Oh great, yeah. Okay, great. We just had to wait a little bit. So now that backend is gone and we're sending 10% of queries to a backend that doesn't exist, the load balancer is now failing over 10% of the queries. Because remember, the other backends also fail about 1% of the time. And now there's a clear gradient in that top right graph now, right? And it corresponds with the increase of the burn rate, which has now exceeded our SLO, or our threshold for page, based on this SLO alert. And the last panel is showing the currently firing alerts in Prometheus. And so yes, we just got page because as soon as the backend died, our error consumption rate increased over our acceptable threshold and the page went off. So great, mission successful. Oh, thanks, slides. I'll just put my things back over here. All right. So I'm very happy that that worked. Last time I did that, it didn't work so well. So I did mention that there's kind of a dark art to picking out the gradients here. So let's say that 70 errors per second is over-paging your team or it's under-paging your team. So you can gauge what that means based on whether the users are calling customer support about your service or your team is doing a lot more work than it seems necessary. So this is an easy knob to turn, right? Because it's a number, and so you change the number up and down, and the gradient, the mechanics behind the gradient alert are still the same, and it's just the target you're picking says what's acceptable to page on. The other magic in this graph is that gap between the two gradients. What happens if the service is burning faster than the SLO, but slower than the page rate? So maybe you set up another one, which is tickets show up, because there's maybe 3 days to respond or a whole 7 days to respond to the burn rate. Well, it's something that does not require immediate human attention, because that's one of the requirements for something that pages you and wakes you up, perhaps. But remember, all these things are forecasts, and so they're a bit, there's a lot of fudge factor going on. So it's easy to modify and not worry too much. So you can set the thresholds high enough that it matters, definitely matters when it's going off, and then you set some fallbacks to say, okay, well, we file tickets and we do a weekly review of whether or not we're meeting our SLOs. And so by doing this and deleting all our other alerts perhaps, we've lost some insight into the way the system works, because previously if you had cause-based alerts, they were very good at telling you what was wrong with the system at the moment the page went off. And we've gotten rid of those because I declared that those are a maintenance nightmare and they're just going to create technical debt. So by removing them and replacing them with this style alert, how do you know what's going wrong in the system? So I want to talk about observability. Not too long, just a little bit. But remember back in the 2000s, you had a single application and like something was going wrong in it. You could just log into the machine, you attach GDB, you can see everything that's going on inside the application. And now in a modern Kubernetes style infrastructure, you might call GDB an application observability sidecar that attaches to the side of the application and solves all of your observability problems, because you can ask questions of the system using GDB. But that doesn't exist anymore because we have distributed systems and there's network boundaries and process boundaries going on. But we still need a way of tracing those call stacks and setting breakpoints and understanding what's going on in the system in order to debug it. So without GDB in a distributed system, what do? Ta-da, observability. So we wrote the metrics into the application, and that's one way we get that. That's how we were able to understand that there were problems in the first place. But there are other techniques, tools we can use, and personally I disagree that there are 3 pillars of observability. I think there's one, and that's all the event, and then the 3 things just happen to be ways of looking at that kind of event. And hopefully everyone is familiar with logs. They print out as text. Maybe they don't print out as specific as just text. They're a bit structured. Maybe you use tracing, or you should use tracing, and tracing is just logs, but with a session identifier in every single log, so you can understand what the sequence of events per particular request is. And metrics are the same as events, but they've already been pre-filtered, and maybe you aggregate them by, you break them down. And the example I used earlier was to say only show them aggregated by user and response code. I don't really have a good use case for how stack traces and exceptions and core dumps fit into this model, so they're a separate pillar. But I want to stress that these tools exist so you can understand the system, and you use your brain at this point to try and debug what's going on in the system. Alerting is not a debugging tool. Alerting is a way of automating the watching the system to find out if something has gone wrong. Because there's this high cost of maintenance for writing all these diagnostic alerts, and it still doesn't help you with the problem of trying to figure out the problem you haven't yet written the alert for. So you're going to have to rely on these tools, or the debugging tools in general, anyway. Observability is an emergent property of your system, and it's not static, because every time you hit a problem and you can't figure out why it's happening, then you know that you can add some more information to debug it the next time. So if the end of your debugging triage is, I don't know what the next question to ask is, or I have the question but I don't know how to ask it of the system, then that can inform you on what features to add to the system, or what additional instrumentation you need. So when you move to this SLO-based alerting, you remove all your cause-based alerts and you replace them with better debugging tools. Because there are always going to be unknown situations, so you need a way to look for clues and ask questions and try and figure it out. Making automatic diagnostics doesn't help the case where you don't know the answer yet, and I believe they are like tests in that they create inertia in the API of the system, and so if you want to be able to change it, then all of a sudden you have all of these alerts that also require changing. I've been on many teams who have changed the way an API works, and then forgotten to remove the alerting, and so they roll it out and all of a sudden the alerts are firing, and you go, what's going on? Oh, it turns out that feature is deprecated and it's been removed. So we just have to remember to remove the monitoring. Great. That was a great use of my time at 3 in the morning. So I do have a caveat, and that's that these diagnostic alerts are good if the cost of maintenance is low, because that's basically the core of my idea. So if you can make infrastructure that exports all of the information in exactly the same way for different types of, say, RPC services, and you have one rule that is doing cause-based alerting for that particular piece of infrastructure, then that's fine. I'm going to let you keep that. But I want to stress that if it's costing you a lot of time and maintenance, and every time something changes you have to go and change that too, get rid of it, because it's slowing you down. The other caveat is that you're probably afraid to try this new technique and delete all your old alerts because this is new and terrifying and the old ones you trust. That's fine also. Start with this in parallel. Start to downgrade the severity of alerts so they don't send pages to people as you gain confidence. And after a while, you've stopped filing tickets, you'll stop sending emails, you might even stop logging them, you'll just delete them entirely, and that's kind of the goal. Something I tried a long time ago was to just make all these alerts that don't page show up on a dashboard, so when you go to start debugging and then you've got your little console with all your graphs, it also says all of the other alerts that are currently firing, and I thought that would be really good as a dashboard indicator for, the check engine light on your car dashboard. Turns out nobody really used them, so you can try it, and best of luck to you if you do, and I really hope it does work, because I thought it was a cool idea. Anyway, I want to stress that I don't go on call for the sake of being on call. I don't consider it the job of the sysadmin to be the one with the pager. I go on call because it's a tool to help the service become more reliable, and it's a tool for improving the product. Alerts don't go away by themselves. They require time and investment of energy and lots of thought to make them disappear, and they only increase in number if they're left unchecked. So you invest in periodic review of these alerts, decide if they are happening more often or they're not adding any value to the service, and you can set goals on these weekly reviews of what acceptable level of paging is. Something in SRE A good rule of thumb is that we say that it takes about 6 hours on average to fully understand the reason for a page. And so that means in every 12-hour shift, you can only have 2 alerts. So that was the threshold we set, was a maximum of 2 pages per shift, and anytime any shift goes over 2 pages, there's a real problem there. So inside Google, we talk about this idea of operational excellence, and that involves things like we have good load balancing, and we know how to respond to our tickets, and our pager load is quite low, and we all know how to debug the system very quickly. To me, it's something that you can make a career out of. And Tamika was talking earlier about there's the skills that stay the same and the technology changes, and that's been something I've believed for a long time, is that like as a sysadmin, running software isn't my goal in life, and making software to run software isn't my goal in life. I want to be able to live my life, and being a sysadmin is just something that I enjoy and am good at, but like that doesn't define me. I also like to go out and spend time with my family and have fun and live a life outside of work, and so not being paged really helps me feel like I'm exceeding at being a sysadmin. I thought I had some more to talk about, but apparently not. So if there are any other questions that you have for me right now, then I've got 2 minutes. And I'm just going to put up this last slide. That's a link to the source code I used for the demo with some instructions if you want to try running it yourself. It's very rough, but best of luck to you. Yes?
To what extent could machine learning help with this problem?
To what extent could machine learning help with this problem?
It seems like still a lot of manual intervention based on sysadmin. We're still trying to figure out what is a problem.
Right. So
Code an algorithm to define the problem.
you want machine learning to help you recognize what an SLO looks like, or you want machine learning to help you debug once a problem has been understood to have happened? Okay. Come to my next talk. I think this is a very deep topic. My personal opinion is I don't think we should rely on machine learning for creating the alert definitions or alerting us based on abnormality detection, because people want to know why they're being paged, and it's very difficult to understand. If a machine has decided that a page should be sent, then we also need to know more about that decision-making process. It's very easy for a human to look at the rules saying, okay, the SLO indicator, sorry, the SLI, service level indicator, has increased at a rate much greater than we expected, and now we can start debugging the system. I think I'm not giving it a great answer, but I feel like if that is kind of hidden behind machine learning, which is kind of magic fairy dust, then a lot of people get a bit, I'm quite uneasy about that. And in my experience, every time people build cleverness into the alerting system, everyone shies away from it and goes, I don't trust it because I don't understand how it works. And the simpler, the better.
All right. Thank you, Jamie.
Thanks, everyone.
Great stuff. And